whatever you do, I can prove it today, so. Okay, so what's in the space around here? A magnetic field. And because the current is going, it's getting bigger and then smaller and bigger and smaller, remember it's alternating current, then the magnetic field is growing and shrinking and growing and shrinking like that. We have another coil of wire over here. There's no contact between them. But this one has a lot more turns of wire on it. Then what's going to happen is the magnetic field of this wire is going to cut across this wire back and forth like that, right? And if you have a magnetic field cutting across a coil of wire, what happens?
Great current.
Yeah, you reduce the current. And what's true about the power in this?
Equal.
Power is the same, but because the resistance is so much bigger, the current is going to be much smaller, right?
And the volts are
voltage.
So, yeah, so if current times voltage here is the same as current times voltage here, the voltage has got to be a lot bigger to compensate for the current being smaller.
And this is the step up.
This is a step up transformer.
So the electricity going through the coil gives it one a magnetic field and two makes it move.
Yeah, because the current is changing,
It goes back. and
then the
forth.
magnetic field gets bigger and smaller.
So it's just kind of like
Yeah,
vibrating, I guess.
right.
And because then the motion of the magnetic field on the current, the next closed circuit is what makes it.
What
generate
induces the
electricity.
current, yeah.
Wait, why did we say that you want to change from alternating, or from, alternating to direct?
Well,
Here rather than the,
yeah, ultimately you want to change to direct current for things like computers and televisions and
Yeah.
anything that gets information. But the point of leaving it as alternating current for now and changing it later at your house is because you want to be able to use transformers. And if we were using direct current, then when we turn the circuit on, the magnetic field would build and there would be a brief pulse of current in the circuit. But once the magnetic field got steady and the current steady, then no more current is induced. So it would just be induced when you're turning on or turning off. Okay, why do we want to make the current smaller?
so we lose less power.
Less power.
Yeah, power loss
more
and
power.
is I squared times R. Yeah, yeah.
Sorry about that. Sorry, everybody.
That's right, you're on film too, so. So anytime we can do something to make this current smaller, that means we lose way less power in the wires. So on the way to your house, there's more of it left for you at the end. Okay? Lizzie?
How do you make the current smaller? Is it because there's, like, the other coil has more resistance?
The other coil has way more resistance, and theoretically anyway, there shouldn't be anything lost in the transfer.
Okay.
So in fact, there probably is. There's probably some kind of thing equivalent to friction that takes a little bit away.
Okay.
But it's still a pretty good trade.
Does the more turns mean more resistance, or is
Yes,
it just
way
does
more,
way
yeah.
more?
And that's why there's less current.
Does that mean that like the wire is actually like doing that, or is that like really really small?
Take
You can't see
Take like a
it.
paper towel holder, and you wrap wire around it.
But that's like
Yeah.
really really small inside of a wire. That's what it looks like inside of like the plastic wire.
These are big things.
Oh, those are in the transformers.
Yeah,
Gotcha.
yeah. They're in those big tin cans. Now, what they probably are is there's one, and then there's another one surrounding it, but there's still no contact in between. There's
Right.
no conduction between them.
That's just so that it can like go emit in all directions.
Right, right.
Cool.
And the closer they are, the better.
Yeah.
So the more you'll get.
Mhm.
And then when you get to your house, and you don't want to have 250,000 volts in the outlet, then you do exactly the opposite. You have a lot of coils and just a few.
Are they all made of the same material? The coils,
Yeah, copper wire.
copper wire.
Yeah. And you step it down. And the formula is the number of turns in one coil. This is, the first coil is called the primary coil, and the second coil is called the secondary coil. The number of turns in the primary over the number of turns in the secondary is the same ratio as the voltage in the primary is to the voltage in the secondary. So it's a really simple little formula. Okay? By the way, before I forget, there's one homework problem that the picture says something different from the written part of the problem.
Which one is that?
It's
The wire?
it's a coil, and it says there are 5 times as many turns, and they're actually like 12 times or something like that. Go by the diagram. And, okay, so that's pretty much what we did yesterday. But I'd like to come back and look at more coils on that video. So,
But for
What?
the homework one, that wouldn't make a difference, would it?
Well, yeah, the answer would be different.
Well, oh, yeah, well, for the second part, when you're doing the actual calculation, but for the first part, when it's asking whether or not it's
step up or step down, it doesn't matter, but, yeah. But I did the calculation using a picture,
Okay.
not using the. Okay, we're gonna go back and look at this, the magnetic field around a coil wire and something called a solenoid. Anybody know what a solenoid is? Oops, sorry.
No.
Ah, well, you'll find out. Circular around it, pointing in the north direction. Okay. Science catalogs. Now we're going to look at a coil wire. Oh, scared me. Yeah, no, it scared me. I get nervous around wires. I don't know why. It was the noise. Okay, now this coil is, I'm connecting the positive here, and you can see underneath, it's gonna go up and over like this, right? Okay, now for the coil, then you have a coil of wire, like this. Current's going that way on the top of the coil. So I put my fingers in the middle of the coil, and my fingers point toward Q, right? So if I put a magnet here, without the current turned on, it's like that, and with the current on, it swings around and points toward Q. You see how the little colored end of the needle points that way?
To the right?
Yeah, to your right. So the magnetic field in the center of the coil is to the right.
initial.
You put it up here, you see that it points to the opposite direction. So it's sort of, if you can imagine like a donut almost. Yeah. Okay. What do you think would be the effect of more current? Because here we have quite a few more. Yeah, it would seem like the force is a lot stronger. Now this one, if you look at the way it's wound, you guys over here can see it. It's wound so that it's coming this way, right? This is the positive coil. Let's see which way. Well, this is negative, and it's coming toward the negative, so it's going this way, I believe, on top. So it's going away from the camera, right? Point your finger, your thumb, toward me. Fingers should curl around in the middle of the coil like this.
Because you told us that the direction of.
You have to know the direction of current in order to figure that out.
Okay, so you told us this way?
The current? The current is coming, I think, I'm trying to see, it's really hard to see. It's coming down, and so it's coming toward me at the top,
Yeah.
right? So if it's toward me and my fingers are in the middle of the coil, my fingers are pointing to the right, to my right. And let's see if that works. It does, and you can tell that this is a stronger field because it really yanked that little needle. It's kind of hard to see, but it's the colored end of the needle that's pointing to the left.
multiply because there's more, basically, every one of those wires carries a current.
So this is direction, the thumb is always direction.
Why does it point to the left?
Yeah, your thumb
Points to the
direction
left.
current,
If you use the
just
right
like
hand rule,
with
you
the
point
other
your thumb in the direction of
And
current,
the fingers are the direction
your
of field,
fingers
but
in the middle of the
force
coil.
involved, so we cover our thumb.
they point to the left.
You want to think that's how it is. Okay, and then the
So
right
it's like the
side.
same sort of thing, like the force is going that way?
Yeah, well, not the force, the field.
Or the field,
But the field is like around the coil like this, right?
Yeah, and because we're talking about the magnetic field around a wire or a coil, we're not talking about forces,
This
so
is
you cover up
positive,
your pond.
and it's wound so that it's gonna be coming.
But it's like the same
back
idea.
in from-
Yeah,
Okay.
Toward the camera. And we're gonna put a couple of pieces in there. And do the same thing. And what you should see now, if the current is going that way from the top, going that way, fingers pointing at Karen again, so we should all swing around and point that way. They're probably close enough to one another that they're having some effect on one another too. I don't, or there are better compasses and this one's not quite as friction free. And what's interesting about this is there's very little field outside. You see that? It's not doing anything particularly with that compass.
So is it inside?
So you have to be inside. This one's pointing north.
So this one's magnetic field is like inside there?
It's pretty much inside. And this is an extremely useful device. It's called a solenoid. Okay? Anybody ever heard of them?
No.
They're in a motor. They're in an air conditioner. There are places like that. And here's the deal. If you have this coil, it has a magnetic field in it, inside it, when there's a current running through it, right? If you take another small magnet and just put it in the middle, then the presence of this magnetic field, when there is a current, will either pull that little magnet in or push it out, depending on what direction you put it in there. So you could fix it so that when the current came on in the solenoid, it shoved the little magnet out and made it contact something and completed the circuit. So something would start working. That's exactly how current. Start a motor and push the button on the, or turn the key, and that sends a small current into the solenoid, which completes the circuit and makes it start moving.
What's the sound of the?
Why does the magnet move back? Why does the magnet move back?
Usually it's spring loaded, so there's a little spring pulling it back in, so when the current goes off again, and there's no force pushing the magnet out, then it goes back in. I don't think there's something like in computers.
So, I've heard there have some kind of magnetic field, like, where they like save the basic data, so you can like store it.
Yeah, but that's printing information, yeah. That's quite as bad to get a magnet, you know, how to get it, because it just erases it.
I think we're gonna stop that.
We have a
So
question.
what did
Cars. What?
How does a magnet complete the circuit? How can a magnet, like, after it gets shot out of the solenoid or whatever, how does that complete a circuit by creating movement?